Okay, we're going to introduce you to matrices. So a matrix is a series of numbers invariably organized in effectively a two-way table. And matrices can be used in a variety of different ways, which to some extent you've never been exposed to in the current math syllabus. They can be used for solving linear simultaneous equations, just as an example. That might have been taught previously, but not anymore. Now, in terms of applied maths, it has its uses in networks and graphs. So this is going to start off by an introduction to the concept of a matrix. We're going to use an example of an adjacency matrix or matrices, plural, and then it'll get used in other ways in other instances in the future. But for the time being, we're just going to use it in the context of the idea of adjacency. So adjacency is the idea of the connections, what are connected to a place. So if we look at the very first diagram we have here, there's three different ones. We'll talk about each of these three in turn. So here's a matrix, sorry, a network where we've got the nodes A, B, C, and D, and we have various different edges going in different directions. So what is A connected to? A is connected to B, and it's also connected to D. It's not connected to C. It's also connected to B twice, whilst it's only being connected to D once. And I could carry on talking about what is B connected to, what is C connected to, what is D connected to. And we can describe this graphic, this diagram, in a numerical format using a matrix. So let's just talk through the creation of this matrix that describes the connections. The edges, basically, is what we're talking about. So going from A to A, well, there aren't any edges that go from A to A. So we're just going to put a naught in that first one. Okay, how many edges are going from A to B? Well, there are actually two. So we're going to put 2 in there. So from A to C, there are none. And from A to D, there is 1. Carrying on, from B to A, there are 2. From B to B, there are none. From B to C, there's 1. And from B to D, there is 1. So from C, you can't go to A. You can go to B. There's nothing where you're going from C to C itself, and from C to D there is 1. And lastly, from D to A there is 1. From D to B there's 1. D to C there is 1. And D to itself there are none. So you can see this grid. Okay, it's 4 nodes. It's a 4x4. It's square. Okay, and you have these. So what you do is you tend to have the rows sort of not headings, but just what it relates to. That's usually the from, and then along across the top is the sort of the to place. So from A to A, from A to B, from A to C. Okay, so from A to D, there's one way of going from A to D. Now, going from A to D is the same as going from D to A, arguably. Okay, it's not a direct graph. We'll talk about those in a moment. So from D to A, that one we see here is exactly the same as the one that we see here. And in fact, if you look at this this matrix, you'll see it has a certain symmetry. If I were to draw a line down the middle, you'll see there's a symmetry either side. So B to A is the same as A to B. C to A is the same as A to C, and so forth and so forth. So that is an adjacency matrix. The labels are only there really to help you know what they refer to. They're not required for the purpose of the matrix, and usually a matrix has 2 brackets. I haven't done that second one very well, have I? Brackets either side, sort of containing the matrix. The labels don't have to be there. Okay, so let's move on. Let's go and look at the next one. So from you got E, F, G, H, and I. Might as well do those in alphabetical order. So we got E, F, G, H, and I. And across the top, we've got E, F, G, H, and I. So from E to E, there are none. From E to F there are 3. From E to G there are none. From E to H there's 1, and E to I there's 1. Moving on, F to E there's 3. F to F there's none. F to G there's 1. F to H there's none, and F to I there are none. Now G to E there are none. G to F there is 1. Now you've probably been seeing this waiting come along. G to G, there's a loop here. Okay, so the loop can be shown because there's an edge going from G to G. Effectively counting edges, basically. Okay, G to H there's 1. G to I there is 1. H to E there is 1. G to F there's none. H to G there is 1. H to H there's none. H to I there's 1. I to E there's 1. I to F there's none. I to G there's 1. I to H there is 1. And I to I there are none. Now again, you can see if you were to take that diagonal, there is a symmetry either side. Okay, so 3 0 1 1, 3 0 1 1, 3 0 1 0 0, 3 0 1 0 0. You can sort of see there's a symmetry. Notice that when there's no loops, okay, that first diagonal, top left, bottom right, contains all zeros. Here, that loop appears because a place to itself doesn't have a 0 for node G. As I said to you, we're effectively counting edges. Now you can make a connection here. So if we think back to the idea of degrees, so how many edges are coming out of E? 1, 2, 3, 4, 5. There's 5 edges coming out of E, and if we look across the top row, so hang on a second, so we can see if I can get this thing to work for me. There's 5 edges there, and we can see the 5. If you add up 3 and 1 and 1, you get 5. Okay, so there's a connection there in terms of the idea of degrees. Now, the only problem that occurs is if we're looking at somewhere where they've got loops. So if you look at the edges coming out of G, is 1, 2, 3, 4. There's 5 edges coming out of G. But if we count up how many edges supposedly coming out, the adjacency of G to other places, there's only 4, a total of 4. So that one loop, okay, that's described by that 1 that's in the middle there. We're counting the edge. There's 1 edge. Now, degree-wise at G, it's coming in obviously twice, either end of it. Just be aware that there are some circumstances where you might have a matrix which will be talking about the degrees. So the idea here is that there's only one way of going from G to F. There's an edge there. It goes straight up from G to F. But there's 2 ways going to go from G to G, because you can go clockwise or you can go anti-clockwise. So there, in certain circumstances and in certain mathematics, it might be a requirement to actually put a 2 in there instead of 1. For the time being, we're just counting the idea of an edge. We're not counting the degrees of edges coming out of a node. Okay, just be aware of that. So lastly, we've got a third one here, and we've got, okay, HI, J, K, L, M, N, O. So we have, oh, don't want that pen. We've got J, K, L, M, N, and we've got O. We're almost running out of space here. Let me just scroll down a little bit. And across the top, J, J, K, L, M, N, O. So you can see there's now 6 nodes. So we're going to have a square matrix which is 6 by 6. So J to J, there is one way of going from J to J. That's that loop that you can see. J to K is 2, J to L is none, J to M, J to N, J to O, and so forth and so forth. And we finished off, and you can see that there are, for example, the loops. There's one loop there, there's one loop there. There's one at J, one at O. And if you look at the symmetry, so if you were to draw a line of symmetry all the way down that middle diagonal, you should find that if we've not made any mistakes, that 2, 2, 0, 0, you can see there's a symmetry either side. You can almost look at the diagonals and just make sure that either diagonal from the center out in both directions is the same. So that is the process of creating an adjacency matrix to describe the edges from one node to another. Okay, so what can we do with matrices now? Very quickly, for a large matrix like these, if we want to do any calculations with these, realistically, you are not going to do it in your head. You're not going to do it even on a piece of paper. You're going to need to use a matrix calculator. I have put in a link to a matrix calculator here. Okay, and you can add in extra rows. So if I wanted to put in that matrix, so with the second drawing, I can just literally just enter in. I'm using a computer here. I don't know what it'd be like using a phone, although, you know, I haven't checked actually, but you might be able to find an app that allows you to input matrices. So I can put in reasonably easy. You should press the tab button to go from one box to the next. So I can add in, that was E, F, G, H, and I, and across the top E, F, G, H, and I. There were loops at E and no, there was a loop at G. Sorry, there was a loop at G. There should be a 0 there. My apologies. There was a loop at G. So that's a matrix, and you'll find that you can do various different things there. You can add in rows. You can do various different calculations. Now, I'm not going to go into determinants and inverses for the moment, nor transposing and ranking. Now, you can multiply by a constant. That might be of use to you, and you can square things. I'm going to talk about multiplication and also putting to the power in a moment, but you can do those calculations quite quickly. So if I want to square that, okay, so let's press squared. There you go, there. So 0, 3, 0, 1, 1, and so on and so forth. If I square that, that's the matrix I get. So I'll talk to you about the process of those sorts of calculations. But for something that's a 5 by 5, I'm not going to try and square that matrix. So it's easier to just use a online one. So let's do some calculations. We're going to concentrate on multiplying for the moment. Okay. What I would say to you is, I suppose I could go through an addition as well in a moment as well, but the main thing we want to concentrate on is the idea of multiplication. So let me just go through that for the moment. So if I want to multiply two matrices together, now, generally speaking, again, for the moment, we're only going to be dealing with square matrices, either 2 by 2 or 3 by 3. In those instances, it's nice and handy, nice and easy, and there's nothing you have to worry about. Just be aware that if you had sort of not a square matrix, but a sort of rectangular matrix where the number of rows and columns isn't the same, when you're coming to multiply, there are certain issues you have to be aware of. Again, we're not going to go through that for the time being. So let's just go through the idea of multiplying two square matrices. So the way it works is, let me just set my highlighter here. We can take the top row of the first matrix and the first column of the second matrix, and we are going to make a calculation here. So let's just go through this. So 2 is the first number in the first row multiplied by the first number in that first column, so 2 by minus 2, I could write that out, and also 1 multiplied by 4, so the second element in that row by the second element in the column. So 1 by 4. And we're gonna effectively gonna add those two answers together. Now you could do that in your head. So -4 plus and +4 is going to get us actually 0. Now, if we then take the first row by the second column, we are going to get 2 multiplied by 3, and we're going to get 1 multiplied by 0. Now when we multiply that, multiply 2 by 3 together, we get 6, add on 1 multiplied by 0, we get 0. So 6 plus 0 is equal to 6. Then, if we would take the second row by the first column, 0 multiplied by -2, and we add on to that 5 lots of, hang on a second, sorry, 5 lots of 4, we end up with -2 plus 20, which gives me 18. And if we take the second row by the second column, 0 lots of 3 and 5 lots of nothing, I end up with nothing. So my matrix at the end of it, when I'm multiplying 2105 by -2, 3, 4, 0, when I do a multiplication, I get a result which is 0, 6, 18, 0. That is the process of multiplying two matrices together. Now let's go and speed that up a little bit for the second one. Now, by the way, very quick, if you're doing any matrix multiplications, you only really expect to do for small ones. You're not going to need to do for very large ones. Anyway, let's go through this a bit more quickly. So I'm going to take the first row in the first column, 3 multiplied by 0, which is nothing, and I'm going to add to that 2 lots of 6. 3 multiplied by 1 and 2 multiplied by 2 is 4. Then -3 multiplied by 0 is nothing, and 0 multiplied by 6 is nothing. And then lastly, -3 by 1 is -3, and 0 multiplied by 2 is 0. So we end up with 12, 7, 0, -3. Now, I just had a quick review of what I was doing there. 0 times by -2, you should realize I made a mistake there. That's 0. So 0 plus 20 is actually, should be 20. My apologies. Anyway, so we get the matrix of 12, 7, 0, -3. Now, a squaring process. So if you think about it, again, as always, it's always good to write out the matrix twice. Don't try and do it in your head with it just written as it is. So if I multiply it all out, as in sort of show the multiplication, now I do the multiplication. So it's 3 0, it's going to be multiplied by 3 1. I'm going to do 3 0 multiplied by 0 2. Separately, I'm going to do 1 2 multiplied by 3 1 and 1 2 multiplied by 0 2. So 3 multiplied by 3 is 9. 0 multiplied by 1 is 0. 3 multiplied by 0 is 0, and 0 multiplied by 2 is 0. 1 multiplied by 3 is 3, and 2 multiplied by 1 is 2. And 1 multiplied by 0 is 0, and 2 multiplied by 2 is 4. So I end up with 9, 0, 5, 4 as my result from that squaring process. If I was going to do a 3 by 3, I won't do all of these, but I'll just go through at least one of them. So I have to multiply all of the first row by all of the first column. Then I'll do it by the second column. Then I'll do it by the third column. Okay. So 3 by 1 is 3, 1 by -1 is -1, and 2 multiplied by 2 is 4. Then if we move on to the next one, I've got 3 multiplied by 2, 1 multiplied by 0, and 2 multiplied by 1. And lastly, I've got 3 multiplied by 6, 1 multiplied by 3, and 2 multiplied by minus 2. So that's the first row of my result. Okay, so my answer would end up being 6, 8, 17. Moving on to the next one, so that now we're going to do the same process, but this time we're going to multiply the second. We're going to multiply the second row by each of the columns. So 0 multiplied by 1 is 0, 2 multiplied by minus 2, 2 multiplied by minus 1 is minus 2, and 5 multiplied by 2 is 10. 0 multiplied by 2 is 0, 2 multiplied by 0 is 0, 5 multiplied by 1 is 5, and 0 multiplied by 6 is 0, 2 multiplied by 3 is 6, 5 multiplied by minus 2 is minus 10. So that ends up being 8 and 5 and minus 4. And lastly, it's a slow process, as you can guess. So lastly, I'm going to take the last row multiplied by each of the columns. So 3 multiplied by 1, minus 1 multiplied by minus 1, and 0 multiplied by 2. 3 multiplied by 2, minus 1 multiplied by 0, and 0 multiplied by 1. And lastly, 3 multiplied by 6, minus 1 multiplied by 3, and 0 multiplied by minus 2. So I end up with 4, 6, and 15 as the final row. So that is the process of multiplying two 3 by 3 matrices together. You have to have your wits together. You have to make sure you don't make the mistake that I did earlier on when I multiplied 0 by a number and got something other than 0. So be really careful about that. Okay, but that's the process of multiplying matrices. And before we go on, I suppose I should demonstrate a couple of other calculations. So I'll tell you what we're going to do is we're going to, what if I can, no, I think what we'll do, just to go through two things. Firstly, if I were to multiply the other way around, so this is what I did in the very first question. That's if you remember, I made a mistake with the 18 rather than 20. So that's the answer to the very first question. So I've now swapped those two matrices around. I'm going to do it the other way around and see what happens. So minus 2 by 2 and 3 by 0. Minus 2 by 1 and 3 by 5. 4 by 0. 4 by 2 is 8. 4 by 2 and 0 by 0. Get your facts right. And 4 by 1 and 0 by 5. So we end up with minus 4, 13, 8, 9. Now, you can see they are not the same. And just to be aware that multiplication of matrices is not commutative. So matrix A multiplied by matrix B is not the same as matrix B multiplied by matrix A. Just be aware of that. Okay, in terms of addition, if we were to do some additions, so it's just straightforward. You're mapping each corresponding part. So 2 and minus 2 adds together to make 0, 1 and 3 adds together to make 4, 0 and 4 adds together to make 4, and 5 and 0 adds together to make 5. So if I had to add those two matrices together, I get 0, 4, 4, 5. So addition is reasonably straightforward. There are no major issues. Just a couple of other things. If I take that matrix of the very first network, okay, graph, we've got that's its matrix for its adjacency. Sorry. So then just very quickly, if I can do a squaring process of that. So if I were to take that matrix, I've already installed it in, and if I were then to square it to the power of 2, I get the answer of 5132 and so on and so forth. So we get a result here for the square, and so I've written that out now. So for what purpose would a squared matrix of an adjacency matrix, what use would it be? Well, if we think about, so it's squared. Okay, so let's think about how many different ways can I get from somewhere to somewhere else in a certain length? Okay, so there are 5 going from A to A. So if you think about your labels, it's sort of A, B, C, D. It's sort of A, B, C, D. There are 5 ways of getting from A to A that has a length of 2. So I can go from A to B and B to A. I can go from A to D and D to A. That's 2 of them. I can go from A to B and B to A, and go from A to B, B to A, and lastly, so the other way around from A to B and that lower edge and back over. So it's 5 different ways. Whilst going from A to B using a length of 2, because it's squared, there's only one, so from A to D to B. Okay, going from A to C, okay, there's 3 different ways I can go from A to C. So I can go A, D, C, I can go A, B, C, and I can go the second A, B, C. There's 3 different ways of getting from A to C using in a length of 2. Now, if I were to do the cube of a matrix, it would tell me how many different ways I can get somewhere with a length of 3. So, heck, why not? Let's just do that for a second. Let's, instead of doing a power of 2, let's do a power of 3. So that's our matrix. And if I were to take just one of these numbers, I don't know, let's just take, oh, blimey, let's take from C to A, which is 3. From C to A, how many different ways there I can do it which involves a length of 3? Right, I can go C, B, D, A, that's a length of 3. I can go C, D, B, A, that's a length of 3. Now I'm trying to think what other. Oh, I suppose I did A, D, B, A using one arc. I can go C, D, B using the other arcs. There's 3 different ways I can get from C to A in a length, a distance of 3. So that's that 3 that I was taking. Okay. So the idea of an adjacency matrix, it represents the edges that connect various different nodes. But in addition to that, you can start looking at certain walks with a certain length. So by taking a square or a cube or any power, whatever that power degree is, that is the length that you're looking at in terms of a distance from one place to another. So going back, there are 15 different ways I can go from B to A with a length of 3. There's 8 different ways I can go from B to D with a length of 3. Length of 5. Okay, it gets ridiculous, but that's the idea. That whatever the power is, that's the length. Okay, that you can take. Let's do 4. So anyway, have a go at exercise 11D. No, 11E. It is, sorry, no, yeah, I am right the first time. 11D on page 214. Have a go, get a sense of creating an adjacency matrix, and then being able to read off that adjacency matrix, and then lastly being able to, you need to practice that process of calculating. I'm going to go at doing some calculations now. In fairness, now just be aware that the only calculations you're being asked to do is where you are being asked to square the matrix. So you should be able to do it for a 2 by 2 and a 3 by 3. You should be capable of being able to do it manually. Feel free to also use the matrix calculator as well to help you. Anything to the power of 3 or more, to be honest with you, you're better off just using the matrix calculator. So get your head around that process of squaring a small matrix and being able to understand the connection between that matrix and the actual graph that you're given, and being able to find then paths or walks that involve a certain length.